of adaptive grid approximations in the weight norm. Author Demyanovich. With of adaptive choice approximation space as variational grid methods in one-dimensional boundary value problems are considered. The result obtained in this work can be applied to the teaching of intellectual computing system with examples, problems with a known solution or with incomplete information about the solution. Numerical examples illustrating the effectiveness of the proposed approach are given. Keywords: adaptive approximation, artificial intelligence. Allow me to greet this present and begin this message. Here I am trying to demonstrate the results using Microsoft's PowerPoint presentation tools. You can stop the presentation anywhere, roll back a number of slides, or scroll forward. The author hopes that these possibilities will be widely used by interested listeners. Due to the limited time available, I suppose to comment very briefly on some of the slides in this presentation. Introduction. There are many studies on learning algorithms. Some of them are mentioned in the introduction to this paper. This introduction is partly presented in this presentation. Those interested can read more about it. I will not dwell on it due to the limited time of the presentation. This work is aimed at development adaptive approximation suitable for teaching intelligent computer systems. In this paper, these methods are developed as a guide to variational grid methods in one-dimensional boundary problem. The basis of this study are the works of Mifflin related to the variation grid methods for one-dimensional boundary problem with generation. See 10. In this study, we consider an adaptive choice of the approximation space where certain information of the behavior of the solution of the mentioned problem is available. The results of this work are adaptive numerical methods suitable for the teaching of intellectual computer systems using representatives of the class of the mentioned problem. The result obtained in this work make it possible to train a computer system on examples of problems with a known exact solution, as well as on examples of problems whose solution is approximately known. Numerical examples illustrate 13, the effectiveness of the proposed approach are given at the end of the paper. In the second section, the fundamentals of the theory of boundary value problems for one-dimensional degenerate second-order equations are presented. The cases of strong and weak degeneracy are considered. As you know, this theory was developed by Professor Miklin. Those interested can read this item in more detail. Then I can show the text here. And here is background. About theory of vision. We will distinguish the following cases: 2, 3, 4, and so on. Yes, that is for mentioned theory. Approximation estimates. Approximation estimates. The third subsection contains approximation estimates needed for what follows. These estimates are characterized by the presence of weight norms. We can see it in theorem first and theorem second. They proved in the text of paper. Approximation estimates without degeneracy. We discuss here the agreed X, C formula 12, yes, and also we have the basic spline 13, formula 13. Theorem 3. We can see the estimate .5 approximation estimate in a problem with weak degeneracy. We have here theorem 4 The fifth subsection is devoted to approximation estimates in the case of a problem with weak degeneracy. Everybody can see it here. And point 6. Estimation or approximation is a problem with strong degeneracy. Here we have theorem 5. I can't comment this theorem because I haven't time for that for it. Point 7. Choosing an adaptive grid. In the seventh paragraph, in the seventh point, the obtained estimates are used to select an adaptive non-uniform grid. The grid is adapted to the code of the variance of the considered problems. General principles for such adaptation are laid down. You can see here grid Y and general situation with condition B. Theorem 6. If conditions B are fulfilled, then the following properties hold. One, two, three, four properties. Theorem 7. The function phi of p, q, z defined by the formula 12. I'm sorry, 20 by formula 20 and 21. This function reach minimum. Reached minimum. Theorem 8. We have estimation 22. I suppose my time is finished, but therefore I try to show next slides on the choice of grid in the case of strong degeneracy. We have certain situation here, see formula 28, and we have equation of third degree 31. Let us whole system of such equations. The point is devoted to the adaptive choice of grid in the case of strong degeneracy. In particular, here we consider the case when P of x is equal to x. The result is a set of cubic equations that can be investigated. The ninth point contains a numerical illustration of the obtained results. Numerical investigation contains results. The problem represented by an illustrative example of the previous point was solved on an HP27 P251 computer using the system Maple 2017 with quantity of points in grid 20, 50, 100, 1000, 10,000. For values 100,000, 10,000, the accuracy achieved was of the order of 10 in minus 4 in degree minus 4, 10 in degree minus 6, and 10 in degree minus 7 respectively. On an information grid with the same number of nodes, node calculations in some cases gave less accurate results. See table 1. Also, the comparison seems difficult because of the differences in the type used computers. Calculation presented in the 11 reference were carried out at Basin 6. Control calculations, the same program using Maple 2021 systems, gave the same results. Table 1. We can see this table here. This is first part of this table and the second part of this table. We can see error at Basin 6 and error Maple 2021. We can see difference between these results. Conclusions. It is widely known that the numerical solutions of problems of mathematical physics have many difficulties. These difficulties are associated with the constant expansion of the set of such tasks. In addition, the requirements to the accuracy of the numerical solutions constantly increase. Using a priori information on such problems, we divide their set into classes of tasks. This circumstance allows the use of trained computer systems for the effective solution of problems. As you know, the training of a computer system is carried out on several problems of this class with a known solution. The results of the learning is determination of the parameters of the adaptive method. Since the solution of the problem of mathematical physics is often carried out various grid methods, finite difference method, then the natural parameters of these methods are grid nodes. The adaptive choice of nodes seems to be very important in the case of problems with particular features of the solution. More engaged into the systems, the method uses a priori information about solution properties for adaptive positioning of grid nodes. In this work, the approach is implemented in the case of the variational grid method for a boundary value problem in the one-dimensional differential equation of the second order. Numerical results of computer implementation of such an approach are done. In the future, it is planned to use this approach for more complex boundary problems. The perceived difficulties are technical nature. One of these difficulties is that the process of learning a computer system requires significant time resources. However, this should not prevent research of this kind, because the power of the emerging computing systems are growing exponentially. We want to give an acknowledgement here and references. The next slide. The references we have here about 14 references. Thank you.